Hello guys, welcome to this tutorial in which we will be looking at how do we load and use pre-trained models. So till now we have in all our previous tutorial sections, now we have seen that how do we work with PyTorch. Now by now it should be pretty much clear that all these layers which are there now can be thought of as Lego blocks, and then you can put them together. The only point that needs to be remembered is there should not be any mismatch in terms of the shape. If that is taken care, now we can easily go ahead and fit things. Okay. Now whether it is needed or not from the perspective of architecture, that is totally a different question altogether, but as per the programming constructs there is nothing stopping us from doing it. The only issue is there should not be any kind of a shape mismatch. If you are taking care of that, you can mix and match all these layers. So now on this specific idea, now let us look into the pre-trained models. Now I am assuming that all of you have the basic idea of networks. I am specifically speaking on different CNNs. So you are comfortable with different networks like AlexNet, VGG, ResNet architecture. Now for the sake of completeness, I will just go ahead into a very brief discussion of the same. Okay. So now let us look into the AlexNet architecture. So now here this is the standard Wikipedia. So this is the Linet now which was developed to take care of the MNIST data. Now you have this 28 cross 28, so the number of channels is 1 now, as you can see it here. So and then you can see that the first convolution has 5 cross 5 kernels, 2 padding. So they have not specified how many filters are there. So since the number of channels in the output has 6, so we should infer that there are 6 filters, and they have not specified the stride. Therefore we should consider that the stride is 1, and then we have a 2 cross 2 average pooling with 2 stride now, which will reducing the spatial dimension by half, and so on and so forth. Now you should be able to read through this. Now this is the AlexNet architecture, now wherein which the input is 224 cross 224 cross 3. So now it should be pretty much clear that why is this 224 224 3 is quite an important number to us. The reason is this is the input size of an ImageNet data. Okay. The first convolutional layer has a kernel of shape 11 cross 11 with stride 4, and then it has 96 filters. Since padding is not specified, so there is no padding, so padding is 0. See, whenever we are not specifying the stride, now we mean stride is 1. Whenever we are not specifying the padding, now it means that the padding is 0, and then we go ahead with 3 cross 3 max pooling with 2 stride. Okay. See, earlier we had non-overlapping pooling, now we have a overlapping pooling. So we should be able to compute the size now based on this using the formulas which we have discussed in our earlier sections. Now so on and so forth, and then you have this ReLU what do you call activation function, and then you go ahead and this is the final size, and that you flatten it out. Okay. So that you flatten it out and convert it into a vector, and then that is converted into a 4096 length vector, and then you have a dropout. For the sake of regularization we are using a dropout of 50%, and then we are using the activation function ReLU, and then again 4096 to 4096 and 4096 to 1000. Now why is this 1000? Now because as I told you, these were the networks that were designed for a 1000 class problem. Okay. So we should have it a 1000 length vector. Now we should get it. Now this is the outcome is the logits, that logits you pass it through a softmax to get the probability vector. So now in this specific architecture, now let us take any other data which is there. Now let us take some other data which has 4 classes. Now then Now the only thing that you have to modify is rather than the final fully connected layer, the classification head now which is having 1000 nodes as the output should be able to give 4 nodes, okay, should be having the 4 nodes. So you should be modifying this last layer, okay. So now on the other hand, if your input size is different, now the preferred choice is reshape the input to match this. Now otherwise all these internal computations needs to be modified, okay. So now if it is not at all possible to change the shape from whatever might be the shape to 224, now then you have to modify the whole architecture. Now then using a pre-trained model is of no use, okay. Now the use of pre-trained model makes sense whenever input shape is 224, 224, 3 and then the number of nodes is the only thing that you are modifying at the last layer, okay. Now this is AlexNet for us, and then one more very important architecture that is being used is VGGNet. So let us look at the original paper itself and then try to understand the configuration of VGG, okay. Now as we can see from this thing, now VGG comes in 6 different variants, okay. So A LRN, this LRN represents layer normalization, B, C, D, E, okay. So now it has 11 layers with layer normalization, 13 layers, 16 layers, 16 layers and then 19 layers. So the input is 224, 224 RGB image, so which is there. In the first layer, now it has a convolutional layer now which is having a 3 cross 3 kernel, okay, and then 64 such filters, okay, 64 filters are there. See here we are not specifying the stride. Now whenever the stride is not specified, now it should be pretty much clear that it is stride is 1 and the padding is 0, that means there is no padding. So the input channel, now we should be looking at from the top, so it is a RGB image, so the input channel is 3, the output channel is 64. Now we should be able to declare the network architecture similarly, and then after that you have this max pooling here, okay. So max pooling they haven't specified the stride as well as the kernel size. Now that means that you should be taking a 2 cross 2 kernel size with stride as 2, the standard one, and then after that you have this the input is 64 channels, the output is 128 channels. So 3 cross 3 kernel with stride 1 and no padding is this layer. Again you have the max pooling. Now you should consider the 2 cross 2 kernel and stride as 2, and then followed by again a 2 convolutional layers. So each of them having 256 filters, now so on and so forth. Now whatever is the output, now finally you flatten it out, post max pooling you flatten it out, and then 4096 to 4096 to 1000, okay, and finally you have this softmax. Now you can see it here, the number of parameters it is in millions. So the number of parameters in A and A LRN is 133 million, in B is 133, in C is 134, in D is 138, E is 144 million parameters are there. Now and this is how we go ahead and work with the VGG, okay. So similarly you can read the network architecture. So I have just taken as a representative VGG 11, similarly you can read these. Now this is VGG, and another famous architecture that we have is ResNet. See the idea of ResNet is coming out of the skip connections. So I am assuming that all of you are comfortably aware the need of skip connection, why is it needed and how does skip connection brings in stability. Otherwise this is the right time for you to look at those ideas. So now the main idea in ResNet is, now you add after certain transformation you add the untransformed data as well, okay. Now that means that the model can choose now whether this particular transformation is needed, okay. So that is the overall idea. So now the way in which it has been done is, for every 2 layers they are giving this skip connection, as you can clearly see from this diagram. Okay, after each of the 2 layers, now you are taking the untransformed input at that point and then you are adding it. So now we can see here that the untransformed data, untransformed input is there, is given. So the transformed data is added with the untransformed data, okay, or untransformed features. Okay. So now like this for every 2 layers, now they will do this. So now let us look at the representations of this. Now the ResNet is famously with 5 variants. Now these are the 5 variants that were described in the main paper. It does not mean to say that only these 5 variants needs to be looked into. Now you can come up with so other variants with, let us say, ResNet 20, ResNet 22 or ResNet 32. Now that is totally fine. Now using the same idea we can come up with different number of layers in this residual nets. So now here you have this 3x3 kernel, and then you have this number of channels, number of filters that are there is 64. Okay. Now the way in which it works is, now first you go ahead with this 7x7 kernel, 64 channels, stride is 2, padding is not provided, therefore the padding is 0, followed by a 3x3 max pooling with stride 2, that is an overlapping pooling that is there, and then now you have this 3x3 kernel with 64 filters. So stride is 1, padding is 0, and the input is 64 channels, the output is also 64 channels, and then it is off. Why is this put in these brackets is, after these 2 there is a skip connection, okay, and like this it is repeated twice. So now the 4 layers here, 4 layers here, 4 layers here, 4 layers here, so totally 16, and this is one 17, and this one fully connected layer now will be there. Now totally this will sum up to number of layers to be 18. So now like this, now we will have the layers. Now similarly you can look at the architectures of different other variants of residual networks. Okay. Now let us try to load these models which are there for our use. Now what we shall be doing is, these trained weights are readily available in the PyTorch library. So they were trained on ImageNet data. Now you can directly use them, and rather than starting with a random initialized random weights, now we can start with these trained weights. Okay. Now that will be good. Now you can think of it like this. So one good example that can be taken on this procedure is, now all of us started, when we started writing 2 cycles, the major issue that we had was how do we balance, okay, but once we transferred from the cycle to 2-wheelers, the main issue was not balancing anymore. Now because the idea of balancing was already learned by us, so we transferred the idea, and this is a kind of transfer learning that we can use. Okay, already we have the weights that can recognize certain features, and on that we can go ahead and fine tune. So now when you go for riding a 2-wheeler, now you will try to understand the mechanics of 2-wheeler. The same thing can be applied for someone who started with a 2-wheeler, which is having these clutch and gear. So when they go to this manual transmission cars, now for them understanding the clutch and then the gear balance will be very comfortable. Now compared to someone who is not familiar with the clutch and then the gear system. Now if they have for their previous things they have only driven some mopeds. So now if they go to manual transmission cars, the major issue for them will be, how do you balance that clutch and gear. But for someone who has already comfortable with that, when they go into the manual transmission car, it will be very much comfortable. Now this is an analogy. So you can think of this analogy now for going ahead and understanding the idea of transfer learning. Now similarly we already have the weights which are learnt on a huge chunk of data. Now ImageNet has 1000 classes and each class has 1300 images. Now apparently the whole data itself is around 200 GB. to train. Now you have a trained weights on such a huge humongous amount of data. Now rather than starting from a random initialized point, now we can start from this and then we can train it. Now at that time we use a different terminology, we call it as fine tuning. Okay. Now because you are already starting with some pre-learned weights. Now these weights are made available to us, so we just take them and then start from those weights. And similarly the next architecture which is there is what is known as a connext architecture. Now in that architecture the main difference is rather than having a 3x3 kernels, now because of which so once you have a image which is of size 224x224, so if you are only looking at a 3x3 it is looking at a very small area. So what they did is they increase the kernel size. Okay. Now you can look out for the network architecture of the connext also. Okay. So now coming back to where we started, now our aim was to somehow load these weights and go ahead and try to do a classification. It can be used for any other task, you can change the head which is there. So now we in this tutorial section we will be going ahead with an MRI data, we will be taking an MRI data, we take this preloaded weights and then we will perform the classification. Now here the number of classes is rather than 1000, the number of classes we have is 4. Okay. Now that means that we should be only changing the last layer. Okay. And we will be reshaping the data into 224x224x3 so that you do not need to change the internal computations. Okay. Now these are all the standard libraries, I am assuming that by now you should be very much comfortable with these. Okay. So now I have defined a simple MLP, so we start with a simple MLP, so which is the image size, the in features is 3 into image size I will specify as 224, so to 512 to 128, 128 to number of classes. Okay. This is a simple MLP just to show the contrast, and then I have used a simple convolutional neural network. Okay. Now I have a convolutional 2D followed by a max pooling, convolutional 2D followed by a max pooling, 3 convolutional networks, 3 convolutional layers are there. So wherein which the first one is having 32 filters, 64 filters and 128 filters, these are chosen at random. Okay. So and then you have a classifier and then head, now which is there to classify it into the number of classes that we give. Okay. So now similarly now I have gotten couple of helper functions to go ahead and load these things. Okay. Now before that maybe it would be a good point, hold on, yeah here, yes, yeah I should have gone here, yeah sorry for that, it's fine, yes, yeah we should have gone from here, that is fine. So now where does these pre-trained models are? Now from Torch Vision import models. Okay. Now what are the models we are getting? We are getting AlexNet, VGG19 and ResNet 18, now all the 3 architectures which we just saw. Okay. So now AlexNet weights so is equal to models AlexNet weights default. Now you load these models, so you get the instance as well as the weights loaded. Okay. Now what is the data that we are using? So we are using this brain tumor MRI dataset, now which is available in Kaggle. I am loading the Kaggle import. Okay. And this is the path in which the data is available. Okay. So now it has started loading all those networks. Okay. So and then here I am going ahead with the transformations, torch, data loader, random split, data sets, transforms, known libraries for us. Now the image size that we have is 224. The train transform, what is the transformation that we are going ahead? Now we are resizing the image to image size. Now what is the image size I have given, which is 224, adhering to the notations that we have. So you resize it to 224x224, and then we have what is known as random horizontal flip. Now these kinds of transformations which are there can be looked at as regularizers. So now what we do is, now we take couple of randomly chosen images and then we perform the horizontal flip. Okay. Now you can also have a vertical flip also, perfectly fine. So just for the demonstration I have used this horizontal flip, and then you convert them into a tensor and then you normalize it with respect to this mean, these 3 means. So this is for channel 1, it is 3 channel image, right, channel 1, channel 2 and channel 3. Now this is the standard deviation with channel 1, channel 2 and channel 3. Okay. Now you go ahead and normalize with this. Okay. Now how did we get these numbers? Now these are ImageNet stats. So this is since we are going ahead with the preloading of the ImageNet data, it would be a good starting point for us. Okay. And similarly, now in the test data, now the transformation which is needed is the shape should match and the normalization should be there. Now we do not normally go ahead with any of these kinds of horizontal flips and things. So test data, we will just take it as it is given. The only thing that we do is the data we will resize it and then we will normalize it. Okay. Now this can be taken it as a small exercise. Now have different stats. Now mean and standard deviation for training and testing data, have it first the same. Now do this and see is there any change in terms of the evaluation metrics at the end. Okay. So I leave it up to you as a small exercise that you can take it up. So and then you are getting where is in the folder, where is the training data and where is the testing data, and then from that you can get the data set. Okay, you just need to specify the transforms. Okay. So now here I just want to remind you that earlier we looked at a way in which we can come up with a custom data loaders, custom data sets. So whenever we specify the index, that is one way, we have an annotation file now which is there and then we go ahead with that. This is another way. Now here in this training folder, now all the different classes are segregated. Okay. So now class 1 is one folder, class 2 is another folder, class 3 is another folder, like that the segregation is there. Now similarly in the testing as well. So now in those cases you do not need to specify and custom data set. Now you can directly use datasets.image folder and then specify the training directory, now from which it can directly take the things. Okay. Similarly train and the test data now you have. Now once you have them, now you can have the validation ratio, you can split them. So okay, and then you convert them into the loaders. Okay. So now you can see here you have 32 in each train batch, the batch size is 32, the number of channels is 3, 224, 224 and this is the label. Okay. So now these are the 4 classes which are there. Okay. So now let us print these models which are given to us. Okay. Print AlexNet, am I using the same variable here, AlexNet model. Okay. Okay. Now if I run this, now you will see this. This is nn.sequential. Now inside this you have all these convolutional layers. After that you have this classifier. Now what is that we have to change? We have to just change this. You have to this whatever is the instance, that instance of classifier of 6. This is what you have to change. Now similarly the same thing goes with VGG19 and ResNet 18. Now that is what is being done here in these. Okay. Now you get the pre-trained models. So you go to this model.classifier as 6. Now whatever is the in features which is there, you change it to in features to number of classes which is there. You get the in features which is in our case which is 4096. Now 4096 to 1000 was there, you change it to 4096 to 4. The same thing is being done for VGG also, the same thing is being done for ResNet also. Now I have used connext also and then I have used VIT. Now as of now since we have not defined vision transformers, now just for the future reference I have just kept it here. Now we can just ignore it and we will come back to this vision transformer now once we done with the transformer architectures. Okay. Now these are the generic methods that we have used and then this is the standard training thing. So and then initialization, so the number of classes is 4. Now your MLP, simple CNN, AlexNet, VGGNet, ResNet 18, connext, tiny and then VIT which is there, all of them have initialized. Now here, now I want to point out that have we used any dictionary similar to that at the beginning of our discussion? There I specifically said most of our usage will be similar to what we will be using later, okay. All the terminologies that we have been using from the beginning, now you can see that starting off the Python we have been consistent with those terminologies, okay. Now because it has to give a 360-degree view of the same idea that will be resurfacing again and again, okay, good. So now you have declared all these things, so I am going ahead with just 5 epochs. So with this particular learning rate I have already run this, okay. So and then what do you do for each of the model, you go ahead and train this model. Now with MLP, now you got around 82% accuracy, okay. So and then with simple CNN that we have, we got 90% accuracy, and then okay, maybe it is not loading. Now similarly, now we can see that okay, maybe it is still training, but that is fine. So maybe it will be loaded. So what we can see here is as the network complexity increases, now we can see that the accuracy improves, okay. That can be immediately seen from this. So what will be the accuracy of VGG, what will be the accuracy of AlexNet, what will be the accuracy of ResNet. Now once you run these, so you can go ahead and compare them, okay. Now this is how we go ahead with the pre-trained loading the weights of the pre-trained models, okay. So now please remember this, the only thing that you have to take care is the shapes, okay. Now once you are taking care of the shapes, now you can use them as Lego blocks and then fit all of them together, okay. So now with this we come to a nice point in which we will stop using what do you call not using, now we will stop discussing all these PyTorch ideas. To an extent we know all the capabilities that are needed for us to be used in our future discourse that we will be going ahead. So now just to give you a small recap of what are the things that we have discussed till now. Now starting from creation of tensors till going ahead and using all these different pre-trained models. Now we have seen CNNs, we have seen RNNs, we have seen how do you load all these pre-trained networks and stuff, okay. So now going ahead we will be implementing all these state of the art generative models, and these are can be thought of as the prerequisite that is needed. And now even if you what do you call ignore the major aspects that is going to come now, because that is what we are going ahead in the course, but these bunch of tutorials which are there starting from the introduction of Python till this PyTorch, this can be considered as one block now wherein which we have given a fairly detailed introduction on Python, NumPy and PyTorch, okay. Now this is where we stop the PyTorch basics tutorials. So in the coming next bunch of tutorials the plan is to go ahead and look into couple of numerical examples, okay. So as we have been repeating that this course assumes that you have already taken a first level machine learning course and then you know couple of ideas. Now we will be reinforcing them. Now till now we reinforced with respect to programming, now we will be reinforcing them again using equations and problem solving skills. That is what lies ahead of us next, and then now we will start with our generative models tutorials, okay. With this I conclude today's tutorial. I hope it was helpful. Meet you in the next bunch of tutorials. Thank you all.